Welcome, Zentnerds. Today I want to try and answer a few questions about thrust fold belts, as several of you, and Nick himself actually, were unsure of their origin. So in order to do this, I'm going to pull from several locations around the world. Here's a slide from the Appalachian mountain chain showing the Laurentian continent approaching the Taconic volcanic arc during the Paleozoic. And you can see that there's an accretionary prism on the west side of the Taconic volcanic arc. And as the Laurentian craton approaches the Taconic volcanic arc, the outermost parts of the passive margin, shown in green here, are going to be stripped off, as shown in the bottom slide by the red dashed lines, and then attached to the upper plate. So while the older sediments attached to the Taconic volcanic arc were originally scraped off the ocean floor, now we're scraping pieces off the continental margin. And we're approaching the rift facies, as shown by these faults here. So this is sort of the general scheme that you're going to see time and time again. Here we are again, just like last time in Taiwan, which of course is the ongoing arc-continent collision between the Philippine or the Luzon arc and Eurasia in China. And the star shows the impingement of the fold and thrust belt against the continent. You can see that, and you can see the thrust going north of that red star. Well, that thing passes right underneath Taiwan, the island of Taiwan. And so all of those rocks in Taiwan, all the high-standing terrain in Taiwan is all allochthonous. It's all transported on thrusts. And the thrusts, of course, are off to the west in this case. They're moving to the west as the margin is being subducted beneath the arc. Here we can see a figure starting at the bottom, where you have the Eurasian continent approaching the Philippine arc, and you're mainly dealing with turbidites and that kind of stuff in the trench. And as time progresses, you're beginning to scrape off material from the Eurasian continent itself, the outer rise slope stuff, and eventually you get to the passive margin itself. And so you've got a whole big thrust belt built up that contains oceanic debris in the very east, and through basement slices and cover slices and quite a variety. But note that all of those rocks are allochthonous and form a fold thrust belt. The arc is exotic with respect to the margin. Here's a cross-section of the Taiwan-Philippine collision zone, and you can see from here the central range duplex, where you have thrusts stacked up on top of thrusts. And that's the area that's being exhumed rapidly. It's the erosional rates in Taiwan, of course, because it gets a ton of rain, are really high. So the stuff just rises like a cork in water. And note the blue line, which marks the suture, passes up and over that. So in this area, the arc's already been eroded. Here's another example from the Himalayas. North is to the left. And you can see again, another duplex structure in the blues, browns, and yellows, which are passive margin sedimentary rocks from the Indian craton, which was, of course, pulled beneath the Eurasian craton in the Himalayas. Again, another example here, excuse me, with the Papua New Guinea. You have the Melanesian arc terrain, which, as we saw last time, was largely eroded. 25 kilometers of stuff has been eroded off of there. And you have the fold thrust belt sitting in front, still high. In fact, at the top of those mountains are still carbonate rocks of the Australian passive margin. And these rocks there are intruded by slab failure plutons 4 million to say 1 million years old. Of course, not every thrust or every fold thrust belt is associated with a continental collision, although sometimes they're associated with big strike-slip faults. Here you can see the San Andreas Fault and an old strand of it known as the San Gabriel Fault. And the rocks in brown here are Precambrian gneisses, probably around 1 billion years old, as I recall. And they're overthrust of the Pliocene sediments in yellows here, shown with all the folds in pink. And those rocks are a couple million years old. And the other rocks are 1 billion years old or older, and they're thrust over right adjacent to the fault. Here's South America. You can see the Arequipa block. South America was pulled under the Arequipa block. You can see the fold and thrust belt out in front of it here. This is from the work of Nadine McQuarrie back in about 2002. You can see all of the thrusts there of Paleozoic through Cretaceous rocks, and there's just a lot of thrusts. And this gets us into how do you make these diagrams? How do you, because you're looking at a surface and you're just seeing a fault at the surface, but how do you make a cross-section like this that looks like it's a whole bunch of caterpillars or something? And let's talk a little bit about how people might go about doing that. Here's a classic paper published in the middle 60s by Bally, Gordy, and Stewart. And they were the first to document, well, maybe the first. They were the first to write it up, really, the significance of basement and a little bit of autochthonous. And by autochthonous, I mean it hasn't been thrust. It's still attached to the basement that it was deposited upon. Sat beneath a detachment which floored all of the thrusts in the Canadian Rocky Mountains. And they pointed out that the start at the bottom here, that you have an undisturbed sequence, and they've marked some points off here, and then a thrust develops as rocks are transported to the east, and then out in front of that another thrust forms. So the thrusts were a typical thrust belt, or a normal thrust belt moves from the in this case from the west to the east, so from the hinterland towards the foreland. And they also showed that there typically was a basin out in front of the thrust, because of course the thrusts are zones of thickened crust. So next to them was a little depressed area which received sedimentation. In this case, they thought all of the mountains to the west were high standing at this time, but we now know that they were arc terrains coming in. They also pointed out how these regions would get eroded. So you have big stack of thrusts and a metamorphic plutonic core, and through time it all got eroded down, and so you just had basically a peneplain, and you had to put it back together. Of course, at this time, plate tectonics was just coming on and wasn't really well accepted yet. And then along came Clint Dahlstrom, who published a very influential paper on balanced cross-sections. And what he did was to point out that the critical thing in any cross-section, since any cross-section is really a model, it's a concept how the geologist sees the structure, because of course he can't necessarily see the structure at depth, but he has to have some way to figure it out. Well, one way to make a acceptable section is to make sure that all the bed lengths in the cross-section are consistent in any given thrust. And that's called a balanced cross-section. And it can be restored back to be a perfect stack of sediments prior to thrusting. But the balanced cross-sections is a key concept, and a major place to learn about that, should you care to, is the short course in geology. You'll find it on the internet if you look for balanced geological cross-sections. It's a bit technical, but it has all the information that you need to work on or to think about cross-sections in successions. And of course, they've been really important, and there's been a lot of work by the industries such as oil and gas to figure out where the traps are for oil and gas, and to then drill down and get them. So you want to know, you got to make good cross sections. But remember, cross sections are models. They're not facts. They're models, and each geologist will portray the way he sees the geology at depth. Now you can also do it by drill core, or if you've later folded the area crosswise, you can look at oblique sections and put those together, and we'll look at those in a little bit. But for now, let's stick with looking at balanced cross sections. Here you can see some thrust sheets forming. Most thrusts have a flat, an area where the thrust travels along bedding. Maybe it's some weak horizon, like a shale horizon in a bunch of sandstones or limestones, or maybe a salt or gypsum horizon. And then, for whatever reason, the thrust decides to cut up section along what's called a ramp, and then it typically will flatten out again. So you can see a succession of thrusts forming again from left to right with time. So the thrusts are getting younger as you go to the right, and you form a duplex structure beneath what's called the roof thrust and what's called the floor thrust. Of course, some thrusts are younger and can cut right across to everything else. Here's an out-of-sequence thrust that doesn't go in the normal sequence of older to younger in one direction. I've colored them, the original fault in red as it bifurcates, and then it gets truncated by that purple fault in the middle. So the purple fault is clearly out of sequence with respect to the normal sequence of migrating thrust faults. Let's now head up to the Northwest Territories in Nunavut in Canada. Great Bear Lake on the left. This is a compilation map at 500,000 that I made of an area called Watmay Orogeny. It's a 1.9 billion year old collisional orogeny. And the Coronation margin is the original passive margin, which sat on the Slave Craton, which is an Archean block. And in fact, the area marked A contained basically the world's oldest rocks, 4 billion years old. And my friend Sam Bowering discovered those, and I was fortunate enough to spend a summer mapping in those rocks years ago. But I also had the opportunity to work in pretty well every area here and mapped a couple of sheets. So this is a beginning of my geological career, so it's dear to me. And what you have is an exotic arc terrain, which I've labeled here as the exotic Hata Klippa, which is just an isolated block, a big giant thrust sheet, if you will. It's the arc complex. And to the right or to the east is the foreland fold and thrust belt called the Asiatic thrust fold belt. Then to the west you have the Great Bear Magmatic Zone, which is a post-collisional arc terrain after subduction flip. And in the left there where it's labeled Hata Lake, you have the main part of Hata Lake, or Hata terrain, excuse me, where I first discovered the Hata terrain itself, which was I think it was about the oldest exotic terrain found in the Canadian Shield. Anyways, one bit of fun that we had there is my friend John Grotzinger, who later went on to work at MIT and Caltech, and also was the chief scientist for the Martian rover. He did his dissertation in the Coronation margin in a formation of carbonates called the Rocknest Formation. And so, but he started having his crew when he was the chief scientist at NASA to name parts of Mars, features on Mars, after features in the Northwest Territories. I had never asked him why he did it, but at any rate, the first conglomerate that they found on Mars, he names called the Hata conglomerate, or the Hata site, if you will, and it's named after Hata Lake, which is also the name that I gave to the exotic terrain that collided with the Slave Craton about 1.9 billion years ago. So it's kind of interesting. Anyways, here's a couple of cross sections done by Rain Tyrrell, whose dissertation was in fact, the Asiatic foreland thrust fold belt. The carbonate rocks are shown in blue-green here. The four deep rocks, the turbidites and fine-grained stuff just under them are shown in orange. The yellow are the basal siliciclastic prism that we looked at last time. So here you can see two cross sections. Things are migrating. The thrusts migrate from west to east. And here's what one of those faults looks like. Here's the frontal thrust with the rock nest formation and the ogic. Note that in general, thrust faults place older rocks over younger rocks, as we've seen before. Maybe you didn't notice that, but here's the ogic, which is the basal siliciclastic unit, and it's sitting on top of the rock nest along major thrust fault. Things look pretty good shape, actually. So I mentioned that one of the ways that you have control on the geology to draw a cross-section is if you have a plunge section, if you have crossfolds. And here's an area. This was a map done or constructed by cross-section constructed by Rain Turrell. And you can see that in the south is the yellow, which are the basal siliciclastics. Then as you go north, you pass through a whole bunch of thrusts with carbonate rocks, various members of the rock nest formation. And then at the top or the north end, you're into the recluse, which are the greywacke turbidites and collisional rocks on top of the carbonate platform after it's been drowned. So this is an oblique section because there's a synclinal axis just to the north of this map. And so you get basically an oblique cross-section and can produce a beautiful, much more robust cross-section where you have some topographic relief, or where you have a plunge section where you can basically look down the plunge and see what the structure looks like. So you can try to envision how you might do that. If you want to do that, one way to do that would be to print this slide out and then hold it almost flat with your eyes and look down the paper, and you'll see the closest approximation to the actual cross-section itself. Note that thrusts are not exactly like pizza boxes, although I understand Nick's idea to use pizza boxes, but they'd be pretty flexible pizza boxes. I prefer to have them be slices of pizza, because whenever I pick up a slice of pizza, it kind of collapses and the sauce spills on my lap and burns me. Anyways, here's an example. Here's that frontal thrust again, with a person circled, and you can see a small crossfold where it's intruded by a mafic dike, much younger mafic dike, by the way. Just to show you what these things look like in the field. Here's the final plunge projection through from west to east through the orogeny itself. You can see the fold and thrust belt in the east, and then as you go to the west, past the shelf edge, where things get a little dicey and it's not really easy to make sections, you go into the metamorphic rocks and eventually into exotic rocks covered with plutons. The Exmouth Massif, which is the farthest of the pink stuff in the lower diagram, is where those acastogneisses, the 3.9 billion year gneisses, are. Well, let's move into the Cordillera, and I wanted to make a point about this area because I think that Nick is going to continue to talk about it. And this is the figure from my Tintina Rocky Mountain Trench paper, and it's important to note that the thrusts labeled 50 million years, 52, 54, 51, 56, are all, of course, within an error of each other because they're mainly the same thrust. But everything else to the west is just being carried in that thrust sheet, and it's all just a whole bunch of jumbled thrusts and normal faults and things that relate to older collisions and so forth. There's not a whole bunch of thrusts to the west of this thrust that are active at that time. However, the thrusts to the east of that in the foothills belt were active in the Eocene in the 50s. And were forming in front of this whole mass as it migrated to the east. Here's a classic map, big fold-out map. It's probably 4 or 5 feet across, by Ray Price and Firmer. And one of the things it shows is the distribution of geology at the surface. And of course, you can see in the orange area, that's the 4D. That's the stuff that moved in front of the migrating thrust of blue rocks. And all of those thrusts to the west were not active at this time. They were older, some as many as 10, 20, 30, maybe even 100 million years older. But the blue rocks are the main big carbonate units that you see in the main ranges in the Cordillera. So if you take, like I said, you need to be able to restore these sections. So here's the section, and they've taken their balanced cross-section and shown that it can be restored, and you can see it above the actual section there. So that's how things fit back together. And you can actually use that to calculate how much shortening there's been in the fold thrust belt. So one of the things that they did, of course, which is just kind of wrong, is to take a whole bunch of different thrusts of different ages, many different ages, 10, 20, 30 million years different in age, maybe more, and included it as one thrust belt, but it's not. There's one major thrust that transports everything to the east at 52 plus or minus 2, say, and over the orange rocks, and those orange rocks get thrust along with the migration of this. So it's really just the amount of shortening in the orange belt that you want to look at. But there are no rocks that are in the thrusts, the blue thrusts, that actually are underneath those orange rocks, despite what's shown here. So here's all those thrusts in what were orange rocks. Now they're colored green in this map. And there's a whole bunch of them, and there's tons and tons of drill core out here, drill holes out here, so they have a pretty good handle on the thrusts and their shape as well. And then as you go west, you hit the front ranges, and that's a completely different package of rocks. And here's what those thrusts look like. And of course, remember, those are all being carried on that frontal thrust. These are all older thrusts. They were not deformed at the same time or even in the same event as the main thrust, which is the McConnell, Livingstone, and so forth, Lewis thrust. Here's the cross sections showing the fold and thrust belt in a little more detail for you. The green and yellow rocks, of course, are those that were colored orange in the first one. And then as you go through to the front ranges, this is the lower section. So looks like a similar style, but it's you can't really tell because a lot of the thrusts in the lower part are older, but yet this cross section was constructed under the assumption that all these thrusts formed a continuous fold and thrust belt. And so they made everything match and fit really well. But anyways, if you go west from this lower section, a little bit farther west, you'd see that a lot of these thrusts are folded, big folds. And these folds are probably 30, 40, at least 40 million years older than the frontal thrust that we've been talking about. And if you go a little bit farther west than that, you'd find this is in this area here, which is right over the Rocky Mountain Trench. You'd find that these rocks are in giant naps, big folds that have horizontal fold axes. You can see it in kind of a teal blue here, surrounded by blue. That's the center of a fold that's been refolded and is got an upper limb in orange and dark blue, and a lower limb in orange and dark blue, and they're all refolded. And the metamorphism is pretty high. It's up to almost melts. It's the appearance of K feldspar and sillimanite, and the grade increases quite rapidly from east to west here. And the structure is very complex. So these are all older structures, though. These big folds, reclined folds like this, are Jurassic. So they're even much older. And if you look at the geology, this is from Mo Kolpron's work. and just more or less in the same area as that last slide. But it's extremely complicated, cut by a whole bunch of Jurassic plutons, so we have a little bit of control on the age of those thrusts. And if you want to look at a cross-section sort of from southwest to northeast, it would look about like this. And there's a lot of detailed work in this, and you can try to figure out how it happened. But it's several periods of deformation, and not just one period. And again, these things are Jurassic and Lower Cretaceous. Let's think about about Europe now, the Alpine orogeny. And I really like this book, the old book, written in the 1930s, called Tectonic Essays, mainly Alpine, by E.B. Bailey. And I'd recommend it to anybody who wants to understand a little bit more about the Alps. It's written pretty, almost anybody I think can understand this book. And it's like I say, it's written in the 30s, so it's a good book. Anyways, you can find it used pretty inexpensively. Another used book on the Alps that I really like is this one by Leon Collett, The Structure of the Alps. And this book was first edition, I think, in 20-something, 1926. This is the second edition, 1932 or so. And he was, I think, a Scottish geologist who did a lot of work in the Alps of Switzerland. And again, another book that you can probably find that's pretty inexpensive, but it was written a long time ago, and they didn't use a lot of the terms in geology that we'd use today, and so it's extremely well illustrated with pen and ink diagrams and so forth. And I can recommend that to anybody who's interested in understanding the structure of the Alps, which is far better known than any of our rocks in the western U.S., by the way. So here's a fold-out figure in the back of that book by Leon Collett. And you can see there's 3 cross-sections through the Alps. You can see these giant nap-like structures, refolded folds, recumbent folds, things that lay on their sides. And the foreland is off to the left of this diagram, which is the northwest, and the lower one. And the hinterland belt, of course, is this area where they have these huge naps. And the Matterhorn's there, for example, as well. Here's a blow-up of the Dent Blanc nap and the Monte Rosa nap and the Great St. Bernard naps, these big, giant structures that sit with the Matterhorn on top in the exhumed hinterland belt. And note, as you go to the northwest and to the high calcareous Alps, again, big, huge naps as rocks were deformed. Now, the interesting thing about this, just as a little sidelight, is when I bought this used book, maybe on a Libris or somewhere like that, and maybe it even came from England, I don't recall now. But when I opened this fold-out at the back of the book, there was a postcard, a picture postcard from the 30s, and it's addressed to Noel Odell from Dr. Collett, Leon Collett, and there he is with his 2 field assistants in Switzerland. I didn't even know they had picture postcards in the 30s, but apparently they did. And it was just tucked into the back of the book. And I thought, wow, I wonder if I have Noel Odell's book. And here's the back of it showing 1932. And he had some kind words and identifies his assistants and says it's a background of autochthonous sediments and so forth. And I don't know how many of you know Noel Odell, but as sort of an aficionado of mountains and mountain expeditions, I knew exactly who Noel Odell was. And so I took this little clip from an article, and Noel Odell was the oxygen guy on the first British expedition to climb Everest, which of course ended with the disappearance of George Mallory and Andrew Irvine as they were getting close to the top of Mount Everest, and then they disappeared into the clouds and weren't seen again until their bodies were found, in the 90s. So, but and it's got his quote here, and as he saw it, and so forth. So I thought this was really interesting that I ended up with Noel Odell's copy of Collett's book on the Alps. And in fact, I don't know whether it was Noel Odell colored it in, but somebody colored in one of these fold-out maps. From you can see the original stuff in the or the original rocks down at the very bottom, and you can trace the history of it through time. And one of the things that's pretty interesting. This is done. This is actually the work of Emile Argan, who was a Swiss geologist back in about 1916. He did this work, but you can see that it has one plate, the western plate there, diving under the eastern plate, and a big bunch of recumbent naps in the middle. So it's very much like people would think about modern tectonics today, in a way. One plate diving under the other. They're not just smashing together. One's diving under the other one. And then the sedimentary rocks in between are all caught up. Another book that I'd like to recommend to people is Ganser's book on the geology of the Himalayas. Another wonderful book, and has some huge fold-out maps, geological maps of the Himalayas and so forth. So you could search for this used as well. And I think I'm going to end there. I think that's enough time. So hopefully you learned something. If you have any more questions, ask away. Go back and review this and just study some of the diagrams, and because I've moved pretty quickly, but I know you can go back and stop and look at any of the diagrams and so forth. So please do that. If you have any more questions, just ask. I'll try to be in the live streams again after Thanksgiving. Enjoy.